Okay, well, welcome to the first video lecture of Calculus and Analytic Geometry 1. The first few of these lectures are going to be intended to be review in nature. Plane trigonometry and college algebra are prerequisites for this course, though I realize some people might have had these things waived for the course because of your advisor or things like this. So I do want to review some key concepts, and then if anything is new to you or perhaps you don't quite remember, I encourage you to go do some extra research on your own, look up some of these things online. If you see any keywords that you don't know, a quick Google search will give you multitudes of references for these sorts of things. The first thing that I want to start off with, though, is sort of an introduction to the course. And it's mainly, the first thing I want to ask is, well, what is calculus? You know, we make people in various majors take this course and tell you that it's important for this, that, and the other, but what exactly is calculus and why is it important? So the answer to this question, there are a number of answers that you could sort of give, but the answer that I will give is that calculus is the study of continuous change. And what I mean by that is there are quantities that we're interested in the world. Perhaps the most simple of these is position as it relates to time. This is one of the things Newton studied a lot. Maybe if I throw a ball up in the air, how does its height change with respect to time? And in particular, one of the things that you notice about that position is that it changes continuously. And continuous, in this sense, maybe that's another thing we can ask real quick. What does it mean for something to be continuous? Or what does continuous mean? Well, we'll rigorously define this later, but for now you can think about continuous meaning smooth and without jumps. Or maybe connected is another way to think about this. So if I were to draw you a continuous graph, or the graph of a continuous function, it looks something like this. It does not look something like this, where I have jumps in the graph. So maybe I'll, not that, yes, this. Color coding the notes because I'm an excellent lecturer. Anyways, so calculus is the study of continuous change and how most of the change that we care about in the world is continuous in nature. And so we want to be able to study that and understand it and be able to make certain claims about those changes. So how do we actually quantify this change? Well, the main way that we do that is through the use of functions. So if you give me a scenario in the world or something which is describing the change of a particular quantity, I can associate that with a function. So that's the first thing that I want to review with you all and make sure that we're on a pretty good setting with. So functions. So we're going to take pretty much anything we're interested in the world with regards to continuously changing quantities, and we're going to write it using functions, and that's how we're going to study it. Calculus studies continuous functions, and that's going to be the focus of this course. So functions. So maybe I'll go ahead and switch up and write this in blue. So the definition of a function, and I'll try to be consistent throughout all my notes with the colors I use for various things. So definition, a function, and there are a number of ways you could define a function, but for us we'll define it in the following way. A function is a rule which assigns, excuse me, goodness, which assigns to each input a unique, this is important, a unique output. Okay, so if I give you a car, well, if I give you a car, you're really happy. But if I give you the scenario of a car traveling down a road and I ask you for its position with respect to time, then we would say that position is a function of time there. And if I give you a particular time mark, it has only one position. We're not dealing with some sort of quantum situation in which things have multiple positions at once. If you want to do that, take a class 5 years from now when you're a graduate student and it's, getting your PhD in physics. Probably don't need to go that high, but anyways. A function is a rule which assigns to each input a unique output. And there are a number of ways in which we can represent a function. And in our situation, we're usually going to use graphs and formulas, but there are a couple of other ways we might do this as well. Maybe I'll go ahead and write this, representing a function. And there are 4 ways that you can do this, which would be tables of values, formulas, graphs, and words. If I describe something to you in words, then you can certainly just call that a function. But we'll really only deal with the first 3 of those. So maybe let me write those down. So tables. So by a table, I mean I'm going to list out the inputs and then tell you what outputs you get. So maybe my input is the day of the week. So input, which is just the day or the day of the week. And my output is going to be the maximum temperature of the day. In degrees, maybe. So input, maybe I do Sunday, Monday, Tuesday, and Wednesday. And there are other days of the week, but we're going to disregard them. How do you spell Wednesday? Always mess up on that one. And the maximum temperature for that day might have been 61 degrees, 65 degrees, 69 degrees, 68 degrees, something like this. And then we're petty Americans, so we'll do it in Fahrenheit, the inferior measure of temperature, but such is life. But this table right here represents a function. The temperature on the right is a function. Temperature is a function of the day, or maybe max temperature is a function of the day of the week. So this we'll not use tables too often, but they may occasionally help us in our understanding. Really the main way that we're going to represent functions is with a formula. So a formula is going to be something of the following form. So let's say my independent variable is x. Independent in the sense of it's going to control what's happening in my situation. Here in my first example, the day of the week was my independent variable or my input. It does not depend on any other variable. So we say that it's independent. So my independent variable is x, and my dependent variable is y. So y here is going to be a variable which depends on the input variable x. That's why we call it a dependent variable. And to emphasize this, we may write sometimes y of x, or maybe you've seen the function notation f of x. What letter I choose to write there is completely arbitrary and immaterial, but this notation is just meant to reflect that y here is a variable which depends on the input variable x. Okay? So examples of this would be things like y equals 5x plus 2, a linear function. Maybe I have y equals e to the x for an exponential function, or y equals 6 times cosine of x plus 7 log x, or something like this. We'll go through what some of these things mean. We'll recap that. But all these mean is, maybe for this first one, is take my input value x, multiply it by 5, and then add 2. So it's just reflecting a rule that you do to an input. So I'm going to take an input, perform some operation on it, and then get my output. Okay? So tables, formulas, and maybe I should be consistent and make this plural. So these are two ways of representing functions. The third way, I need a new piece of paper for this. The third way is going to be with graphs. And this course is called Analytic Geometry and Calculus 1, and so graphs really help us with the geometry part of that title. So graphs are going to be, yes, I have the Zoidberg whoop as my text tone. Anyways, I should actually mute my phone real quick. Okay, so graphs. Well, they are as their name suggests. So I may write something like, oh, I don't know, maybe the x, or the independent axis is t, which is going to be time in seconds. So typically we write the independent variable on the x-axis and the dependent variable on the y-axis. So t is time in seconds, and then the dependent variable is going to be height in feet, above the ground maybe, and this is going to be the height of a ball thrown. Thrown upwards, maybe. And so maybe I start at some point right here, because I am not just sitting on the ground, and I throw my ball up, and as time elapses it goes up, and then it comes back down. Okay, so this would be a graph which represents the position, or the height of a ball as a function of time. So here height is a function of time. And if my height is, if h is equal to height, so I define these variables, h equals height, t is time, then I might say something like h is a function of time. So h equals h of t. H is a function which depends on the time. Okay, so these are the three main ways that we are going to represent functions. Again, I could just tell you what exactly a function is with words, like take the input value, multiply it by 5, and then add 2, or something or other like this. But I think these will be sufficient for everything that we will need to do. Okay, so those are the ways of representing functions. The next thing that I want to talk about are some very common functions that come up. So maybe toolbox functions or essential functions. So toolbox, essential, common, important, however you want to, describe this. But just things that come up very often that we should be very familiar with. So there are 6 of these mainly that I want to talk about. And the first of these are polynomials. So polynomials are functions that look like 5x squared plus 2, or 6x cubed plus 2x plus 1, so on and so forth. Things that look like this. Their graphs are continuous everywhere. They're all connected. So if I were to draw a graph of a polynomial, it might look something like, something like this. I don't know. There's a number of ways that we can do this. We can have the classic just x squared function, which looks like this. But yeah, these are the sort of the graphs of polynomials and what they look like. There are some important features of functions that we're going to need to describe, and to do that, let me actually make a definition real quick. I should have done this before writing out this first example, but oh well. Did I use blue before? I believe I did for definitions. So definition, two things that we need to know about a function are its domain and its range. So domain is all the, I was going to say possible, but all the valid inputs to a function. For instance, the domain of the square root function is going to be the real numbers which are positive or equal to 0, because you can't take the square root of a negative number. Or at least you can, but you need to be in another course to do that, and we're not going to deal with that here. So domain is the set of all valid inputs to a function. Range is going to be all the possible outputs. All the possible outputs of a function. Okay, so these tell us what values are we allowed to put in and what can we get out from putting those values in. There are some notational things that I want to make sure we're also good with. So notation. So if I write something like, and this is interval notation, so if I write something like the interval from a to b with square brackets, what this means is that this is the set of all values x, which are real numbers, such that x is between a and b. And I'm allowed to include the points a and b. I might also write something like a and b with parentheses instead of square brackets to mean almost the same thing, but I'm not going to include the endpoints. So x is strictly between a and b. I'm not allowed to include those points. So if I were to write, square brackets -5 to 2, it just means all the numbers between -5 and 2, including -5 and 2. Also, the notate something like this and this, where I put a square bracket on one side and a round bracket on the other, or parentheses on the other. These have their obvious meanings, where you don't include a but you do include b, or you include a but you don't include b. Have obvious meaning. That is, I'm not going to rigorously write out what these are, but you can imagine what they represent. Okay, so those are the domain and range of a function and some notation. So typically when we specify a domain and a range, I'm going to use this interval notation to do that. So for polynomials, if we go back up top, the domain is just going to be all real numbers. And there are a couple of ways we might say that, but I'll just use the notation -infinity to infinity. We don't include infinity, it's not a number, so we'll use round parentheses there. But it's just saying all real numbers, -infinity to infinity, or I might write sometimes a double barrel R for just meaning all the real numbers. The range can vary. So if I have, yeah, so I could really get into a couple of things with this, but the range, we'll just say for now it varies. And we'll do some specific examples. Well, let's actually talk about some specific examples of polynomials. So I'm about reaching the bottom of my page. So examples of polynomials where I've specified the domain and range. If I have something like, let's see, x squared plus 1, then the domain is again just all real numbers. This never changes. But the range, notice that if I square a positive number and then add 1 to it, x squared is always positive. And so when I add 1, I'm going to get a number which is always at least size 1. So the range here is going to be 1 to positive infinity. Likewise, if I had like x cubed, then domain is still the same. If I write this notation with 2 lines and 2 lines like this, it just means take the above thing and put it right here. But the range of this guy, if I cube a negative number, then -1 times -1 times -1 is going to be a negative number. And if I cube a positive number, I get a positive number. And so here the range is going to be all real numbers. The main thing that's going to control this is the degree of the polynomial. So go ahead and write that down as another definition. The degree of a polynomial is the highest power of x appearing in the polynomial. So in this case, we would have x squared as the highest power appearing, and so 2 would be the degree. Here, 3 would be the degree. If I had something like x to the 7th plus x to the 6th plus 5x squared or something like this, then 7 would be the degree of that polynomial. So it's just the highest power of x appearing in the polynomial. If the degree is odd, then I'm going to have the range being all the real numbers, and if it's even, then it's going to be some subset of the real numbers like this. We won't really need that too much, but might as well just say it here. Okay, so that's everything I wanted to say about polynomials. So the next kind of function that I want to talk about are exponential functions. So exponential functions are these kinds of functions which are basically, exponentiation is the iteration of multiplication. So an example of an exponential function would be like 2 to the power of x, or e to the power of x. Here e is this number which appears on your calculator as like 2.71 whatever. A very important number in calculus. We'll get to that later on. But the graphs of these things, they model, well, exponential growth. So, you know, they sort of look something like this. I should have drawn the graph continuing on both sides. They always pass through, if x is equal to 0, anything to the power of 0 is 1. So they always pass through this line unless they're scaled by something. But they look, you know, roughly like this. I may have something like an exponential decay as well if x is a negative number. Okay, so they look something like this. They represent iterated multiplication. The domain of these guys without any other transformations are going, and we'll get to transformations in the next lecture, but the domain of these guys is going to be 0 to, oh, I'm sorry, this is just going to be all real numbers, because I can take any real number and put it in as the power of x right here. And the range is going to be, well, you can sort of look from the graphs. I can go up to whatever positive number I want, so it's going to go up to positive infinity, and then it's going to decay down to 0, but I can never actually get to 0. So it's going to be an open parentheses with 0 and infinity as the upper limit of the range. So those are the domain and range of these functions. And then maybe let's go ahead and recap some of the important rules with manipulating these functions. So rules for exponents. And the next kind of function we'll talk about is the logarithm function, and those also have several rules which correspond to these rules. So rules for exponents. So let's see. If I have a something like a to the b times c to the b, then this is the same thing as multiplying ac together and then putting the b inside, or putting the b outside. If I have something like a to the b times a to the c, now the base is the same, then this is the same thing as adding their exponents. So this is a to the b plus c, where I've added the exponents up in the top. Same thing if I have division. If I have a to the b, that does not look like it's in the exponent. If I have a to the b divided by a to the c, then this is the same thing as a to the b minus c. And then lastly, if I want to do like two exponentiations, I could have a to the b to the power of c. That's the same thing as multiplying the exponents. So I have a to the power of b times c. Okay, so these are the main rules for exponents that we're going to use. And good to be familiar with these. We'll do a fair number of manipulations involving exponents, so just make sure to understand how these things are playing around with one another. Okay, so polynomials, exponential functions. The next kind of function that I want to talk about, and this is going to be probably a little bit of a longer lecture, but good to recap this stuff in any case. So the next kind of function we have are logarithms, or logarithmic functions. So these are things, when you write them out, they look like the natural log of x, the base 10 logarithm of x, or log base 2 of x. If you're a computer science major, this would come up a fair bit. But they look like this. And if I were to draw their graphs, so axis, then as x goes to 0, well, logarithms are the inverse of exponents, and so it's going to look something like this, where it has a 0 at 1. And what exactly is a logarithm? So I've sort of written down what they look like if you write them down, and then what their graph looks like. But what actually is a logarithm? Well, if I write log base b of a, what this is asking me is b to what power equals a. So that's what a logarithm is asking me. So if I say maybe log base 10 of 1,000, this is equal to 3, because 10 to the power of 3, whenever you take 10 to a power, you just put that number of zeros on the end. 10 to the power of 3 is equal to 1,000. Okay? Same thing with log base 2 of 16. Well, 2 to the power of what is 16? 2 to the power of 4 is equal to 16. Okay, so that's what a logarithm is answering. It's answering this question, what happens, b to what power is equal to a. Okay, so rules for logarithms, these correspond to the rules for exponentiation, or rules for exponents. So we have that if I take the logarithm of the product of two things, then this is the same thing as their sum. And again, I could get more into detail about how logarithms are the inverse of exponents, but this is meant to be a review, so if this is not familiar to you, you can go look up some extra information on this. I just want us to be able to do computations with these things. So logarithm of a product is the sum of the logarithms. The logarithm of a quotient is the difference of the logarithms. And then if I have and the logarithm here, I haven't specified the base of this thing, but these are true for any base that I put in, namely any power of, or any base b that I were to put right here. This b and this b are not the same b. But these are true for any base you put in. So if I take the logarithm of a power, so maybe a to the power of b, then what happens is that b comes out in front as a scalar. So this is equal to b times the logarithm of a. And then lastly, I want to illustrate that the logarithm is the inverse of exponentiation. And so if I say log base b, so here I'm going to specify the base, and I say b to the power of a, well, remember, this is asking b to what power is equal to b to the a. Well, that's just going to be a. So it's going to undo this exponentiation. And the converse of that is if I say b to the power of log base b of a, well, this is just going to be a. Okay? So again, I can undo logarithms with exponentiation, and I can undo exponentiation by taking logarithms. Okay, so oh yeah, let's go ahead and specify the domain and range of these functions. So domain. Well, you can sort of see from this graph, if I say, log base b of some number, so log base b of a is b to what power equals a, well, I can't really take any positive real number and raise it to a power and get a negative number. Nor can I get 0. So that's sort of reflected in the graphs of the exponents that we saw earlier. So the domain is going to be 0 to infinity. So I can only take positive real numbers. And then the range is going to be, well, all real numbers. You can see that it's going to shoot down to negative infinity on this side, and then it's going to go off to positive infinity on the above the x-axis on the right-hand side. So notice that the domain and range are the exact reverses for the exponential functions. So logarithms are the inverse of exponents, and that's one of the main things to know about them, as well as these sort of computational rules that I want us to be familiar with. Okay, so those are logarithms. The other kinds of functions that we're going to deal with are trigonometric functions. And trigonometry is a prerequisite for this course, so I don't want to get too much into this. Trigonometric functions, or trig functions for short. And these are things like sine of x, cosine of x, tangent of x. And I'm not going to tell you exactly what these things rigorously are, but let's at least be familiar with their graphs and then their domain and range. So if I were to graph sine of x, for instance, so this is going to be sine of x, then this is going to range from -1 up to +1, and they're periodic functions. Their period is 2 pi. So if I have -pi right here, -2 pi, and I have pi and 2 pi, then sine of x looks something like this, where it has zeros at the integer multiples of 2 pi, and it's going to hit 1 at the half values of pi. Well, plus or minus 1. Okay, so the domain of sine of x, and for cosine of x looks very similar. We'll just go ahead and draw that real quick. -1, +1. It's going to be cosine of x. This looks very similar, except that its zeros are at the half multiples of pi. And it's going to equal 1 or -1 at the integer multiples of pi. So something like this. Again, the main thing I want us to know is what their graphs look like, and then what are the domain and ranges of these functions. We'll get into some other properties of these functions later on, but for now, we'll just content ourselves with this. Tangent of x, I'm not going to draw the graph of tangent of x. You can put it in on a calculator or some online graphing thing and see what it looks like. But the domain and range of at least sine and cosine, these are the main functions that we're going to deal with, sine and cosine. The domain is just all real numbers. You can see that these are periodic functions, and so I can put in any real number I want, and it's just going to continually oscillate along the real line. So the domain is -infinity to infinity, and the range, well, you can sort of see from the graph it ranges between -1 and 1, inclusive. It can actually attain the values -1 and 1. Okay? So those are the trigonometric functions, at least the sine and cosine functions. Tangent is a little bit different. Its domain and range are slightly different, but we might get to that later on. Okay, so polynomials, exponentials, logs, trigs, and the last couple of functions that I want to look at are the rational functions and the absolute value functions. So rational functions these are quotients of polynomials. So p of x divided by q of x, where p of x and q of x are polynomials. Okay, a general sort of rational function, the graph is a little bit difficult to draw, but you can maybe plot these on your own. Maybe let's look at, I don't know, examples of rational functions would be like 5x plus 2 over x minus 1, 6x squared plus 2x over 3x squared, so on and so forth. They're quotients of polynomials. The domain and range of these things, well, the domain is going to be all the real numbers except where the denominator is equal to 0. So all reals except where, well, the denominator I've denoted by q of x, so I'll say where q of x is equal to 0. So if the denominator is 0, I'm dividing by 0, and I'm not allowed to do that. That's not a sensible thing to do in at least this course. So we're going to exclude from the domain all the points where the denominator is 0, and the range, Well, the range can sort of vary. And it varies sort of in the same way that the polynomials vary with even and odd degree. Okay, so I won't get too much into that. And really the important thing from all of these, domain is really the more important thing that I want you all to know. I want you to understand what values am I allowed to put into these functions. Okay. And I guess I just remembered another kind of function that I want to do for you all, and those are the sort of fractional powers. And really just like the square root function and the cube root function. So something like the square root of x or the cube root of x. So these being the inverse operations of squaring and cubing a number. These are respectively x to the 1/2, x to the 1/3. So square root of x is equal to x to the 1/2, cube root of x is equal to x to the 1/3, just two different notations for writing these things. The domain of something like this, again, it varies the domain here is going to vary depending on whether or not the exponent, the denominator of this exponent is even or odd. Just as the range of polynomials varies depending on the degree, the domain of their inverse functions, like this, is going to depend on the denominator in this fraction. So really, let's just look at these two right here. So square root of x, this is going to be all the positive real numbers. And for the cube root of x, this is just going to be all the real numbers, because I can take the cube root of a negative number. I just get a negative number back out. And in the range for square root of x, it's going to be, well, just as the domain is only positive numbers, I also only get positive numbers out, possibly 0 too. And with cube root of x, again, I can get all real numbers. Okay, and maybe let's go ahead and sketch the graphs of these things. So something like this, something like this. So the graph of square root of x looks something like this, and the cube root of x, which won't come up quite as often, looks something like this. Okay, so these are the fractional powers that we might deal with occasionally. Really, cube root and square root are going to be the ones we encounter the most often, if we even encounter the cube root. You could do, any fractional number up here that you want, but anyways, we'll stay with that for now. The last kind of function that I want to talk about is the absolute value function, mostly because it's an important example for certain things that we'll talk about later. So the absolute value, will typically denote this by the absolute value of x with two bars around it. So all this does is, so let's see, if x is positive, then the absolute value of x is just x itself. And then if x is negative, then the absolute value of x is equal to negative x. That is, if I have a positive number, the absolute value of a positive number is just the number back. And if I have the absolute value of a negative number, then throw away the negative and just give me the positive part of it. So, for example, the absolute value of 5 is 5. The absolute value of 6 is 6. The absolute value of negative 7 is positive 7. Absolute value of negative 8 is positive 8. And also the absolute value of 0 is just 0. We define it to be 0 when we're at 0, when x is equal to 0. And the graph of this is very easy to draw. It's just sort of a simple V shape. And again, I'm not actually labeling all the units on these things and showing you particular points. If you want to see that, you can go graph these on something like Desmos or Mathematica or Wolfram Alpha, any number of things like this. But that's the graph of the absolute value of x. And its domain is, again, all real numbers. Kind of clear from the graph, I can take the absolute value of any real number. And its range, I'm only going to get positive numbers out, or 0. I can include 0 there. Okay, so those are all of the main functions that I want us to be familiar with, and that will come up quite often in the course. Again, there are some computational rules with exponents and logarithms that we should also be familiar with. And then I want us to also understand how to compute with sine and cosine, at least some friendly values. So know how to compute things like sine of pi over 2, cosine of pi over 3, or at least be able to put them in your calculator and tell me what you get back out. Okay, so that is, I think, everything I wanted to go over in this lecture. In the next lecture, we'll talk about some other properties of functions. Importantly, we'll talk about continuity, and we'll also talk about how you can take functions and get other functions out of them. So maybe how to transform functions, how to compose functions, things like this. But that's everything for this lecture. See you guys in the next one.